and it didn't work so well, which was kind of a bummer because I know, because this really delicious. All right, let me start this. Everybody's here, but geez, I was huge for a second. That was freaking. Just in case anybody wants to look back. You're so big,
Once your subway, Jared.
It's National Puppy Day, in case you didn't know.
I didn't know.
Now you know.
I didn't know.
Hey, Michael, when is National Kitten Day?
I can't say that I know that either.
Do you even love it?
I do.
I question this now, Michael.
Okay.
Ozzy, leave it. Come. Come on. Okay. Come here. Hey. Can't just go running around. What is that? Kitten Day? All right, guys. So let me get y'all's. I know I do that every time. I mean to hit this button. I swear to God, I'm not stupid. So yesterday I finished all of your class slideshow notes through the end of the year, so that made me very happy. I'm actually spending some time right now. I've got a couple of you who, hang on. I have a couple of you who needed recovery plans. So those are getting done. And then that's if you have below a 70 and you need an opportunity to catch back up. And then, hang on a second, Alex, I see you. And then I'm working towards getting the finals written up and all of that. Yes, sir. Let me guess, you found an error. Yeah, how'd I know? I knew you were going to say that. How did I know that? I'm psychic.
Well,
Okay.
there's one of them is in the email you sent to me about which grade would get dropped.
Okay.
The final one, there's no space.
There's no space. Yeah, it didn't do that. I had to do them manually. So I think you were the first one, and I didn't notice it till I sent it because you're
And then
alphabetically.
there's also one
the
in the
beginning.
binder.
Oh, what's in the binder?
Let me go get my binder.
So that will give you guys 2 more, huh? Dude is good for brownie points. I'm telling you.
I mean, we're not. We're okay because we're getting brownies.
Right? It's all good.
No, you don't want.
What'd you find?
Your story must onto a single-sided paper.
Oh, wow. You found one of them a long way back. Good. Thank you. That's excellent.
From down.
All right.
Hey, brownie points.
I'm going to add him right now before I forget him. You do.
And then there's also if anyone hasn't caught it, then there was the email sent last week had a TP instead of 2 TO.
So that's 3.
No, I caught all 3 of them on accident.
He's very good at, you need to be an editor. Like seriously, you need to be an editor. And I could never be, actually, I see it in other people's writing, but I don't see it in my own. It's totally an ADHD thing. I just don't see it in my own stuff. All right, so guys, looking at your lesson, right? Are we good? So looking at your lesson, you're gonna complete your Unit 8 test now, and that'll be over break, right? Gonna get that done over break. You're gone for 2 weeks, so you have lots of time to get it done and get it back. And everybody should have gotten, as Alex was saying, an email from me that told you which of your grades that are currently in my grade book, so Q1, Q2, Q3, whatever your lowest scores were being dropped. If you didn't have anything in that spot, you didn't have a score that was low enough to be dropped. My system was, I had it set up to drop lowest 2 tests, drop lowest 1 lab, but it was doing it per quarter, which is not what I wanted it to do. So now I've got it organized so that I took it out entirely and I'm going to do it manually. So after you have completed your last exam, I'm going to go through and, I'm going to go through and do that manually. And if you've already got, if there are zeros, I'm going to do them ahead of time. The only ones I'm going to leave are scores that are actual numbers that are higher than 0. Because there's a chance you could score lower on the final, although no one was going to do that, I'm sure. You guys are going to ace it.
Miracle child.
You're going to ace it. You're going to ace it. All right, so today's lesson.
Wait, you can just drop the final if you want to?
I mean, You could, but I don't think your parents would like that very much.
It'd be kind of funny though.
You could. I mean, and they do that in public school, right? If you have an A in the class, you don't have to
No,
do
they
the
did that.
midterm or,
No,
yeah,
No,
they
they
do
did
that
that.
a lot.
not a lot.
Yeah, they still do it, Cole. Oh, they do. They'll say, oh, if you have an A in the class, you don't have to take the exam. Which is so,
Oh,
That's not
that
how we're
was-
working here though, is it?
no.
Oh.
I mean, you could, because you know a test is going to be dropped. So, I mean, you could be like, I'm going to strategically say no. But the thing about the final is it's the one that's the most comprehensive. It looks at retention more than the other tests do, because it says, this isn't what I just learned, but this is what I learned for the whole year, right? So that, you know, I already gave you some Clementine. You can look at me like that all you want. Do I need to swap those yet? Yeah, probably.
Awesome.
I'm gonna turn these two test tubes around because we're gonna do the synthesis of water with these. That one does not wanna. What's up with that? And the other.
Hey, bro.
Oh no! Oh bye. I think this battery might be dead. It's probably not doing very well. I'm trying though. All right. So I tried to give you guys some historical perspective this week because some of this is a bit dry. So I'm trying to give you some fun stuff too. Not frog legs this time though. Although that was admittedly kind of cool. Very interesting. I thought it was cool. You didn't like the frog legs?
I liked it.
Oh, you did like it. I thought it was hilarious, but
I thought that guy was really.
it was just me.
Close to Magic Christmas.
I mean, what kind of weirdo? Can you imagine just though strolling by your friend's house, it's got frog legs hanging on the fence? I mean, just hanging out there.
Like I said, it'd probably be more normal.
Could be.
Now, yeah.
So I wanted to give you guys some historical perspective on electrochemistry because some of it's kind of interesting because there's an interesting time gap. So here's the here's your interesting time gap is that Thales of Miletus, who was 650 to 546 BC, he's credited with the discovery that amber, when rubbed with a cloth or fur, acquired the property of attracting light objects. So what was he observing?
Static electricity.
Yeah, exactly. What's amber? Do y'all know what it is?
Tree resin that's
That's
crystallized,
Mm-hmm.
basically.
Yeah,
That's it.
it's dried up. And yeah, so it's tree sap, tree resin that's dried up and become hard, and it's now like a stone. And it is used in jewelry and stuff. And sometimes it can preserve organisms, which is really cool.
Like
They get
the
stuck,
dinosaurs.
like in Jurassic Park. Do you remember? Yeah.
And that one's solo.
Mm-hmm. And amber is the color amber, right? Which is kind of that golden yellow color. Ah. All right. There we go. Isn't that John Williams? I think John Williams is that one. So anyway, so the word electricity comes from electron with a K there, and that is actually the Greek word for amber, which seems completely detached from the whole concept that we know of electricity, electrons,
Well, because it was discovered about
Mhm.
after
because he discovered what he discovered about amber. So
reasons.
reasons. That's why, because
Words.
reasons.
Wait, there's logic.
Mhm.
There's actually logic in it.
Yeah.
So.
So this happened 640 to 646 BC was this dude's lifetime. This was way long ago, right?
Wait.
All right, then.
It says 640 to 546.
BC.
You said 646.
Oh, you're correct.
Brandon's putting me on. I think so.
That's not a point.
No, I know. But you should have let me have it.
So then we move all the way. Y'all get? Then we move all the way into the 1600s. We've made a heck of a jump. And we have this dude, Otto von Guericke. You gotta love these names. Otto von Guericke. And he invented the first electrostatic generator. And this was in 1675. So think about this, in 1675, which wasn't all that long ago, really, we're just now getting a electrostatic generator. So we went from like roughly, 600 BC to 1600 before we had any major advancements here.
Does anyone else notice how it went from normal space into big spaces?
Yeah, I'm not sure. I think it's because it's justified, you
I saw
know,
that too. I was like,
left, right, justified. So
But you're gonna call it.
So he made a sulfur ball. The ball, which rotated in a wooden cradle, and the ball itself had to be, the bullets have had to be rubbed by hand and then charged. And then that had to be transported to the place where the electric experiment was carried out. So this was quite a process, right? So that's, I think, a drawing of his little apparatus. And I don't know if the thing, I think the thing at the top is another ball that he's going to use. And he's just farther away or something, so it's smaller. It could be something he's rubbing the ball with. To be honest, I don't know. It looks like a funky lollipop. But if you look at him here in the top picture, he's a bit stuffy looking dude. Now, when we get to Faraday, Faraday is like the man of fashion. I love me some Faraday. But this dude's a little stuffy looking. I mean, look at that face. Yeah, stuffy.
Look at that hair.
So eventually a glass globe replaced the sulfur sphere used by Gerke, and later large discs were used. So this is the glass sphere here, and then this is the large disc. Now this is super cool to me. This is very kind of steampunk, funky looking, and there are sometimes reproductions of these in museums and whatever, and you can see them, but that is, I don't know, it looks like some, I don't know, I don't want to say a torture device, but it looks like something nefarious to me, but I like it. I think it's really neat. Really, really cool. So then we get to this dude. Now we're around 1745, and we get to Ewald Jürgen von Kleist. Now, Ewald Jürgen von Kleist
I can definitely see.
invented the Leyden jar. Now, the Leyden jar is important because the Leyden jar could actually store charge. So we've never been able to store it before. So it contained water or mercury, and it was placed on a metal surface with a ground connection. So what's with mercury? What's the deal with mercury?
Not good to touch.
Yeah, you don't want to touch it. It's toxic, right? So what is, at room temperature, what is its state of matter?
Liquid.
It's a liquid, but it's a metal. So it's similar to, like, I have some gallium upstairs.
That's
You
not
can
quite the same.
put gallium in your hand and roll it all around, and it's not toxic, but mercury is.
But keep gallium away from aluminum. It
Aluminum,
just
yeah.
wrecks aluminum.
Yeah. So, anywho, in 1746, the Leyden jar was independently invented by this other guy who is Pieter von Mussenbroek.
Oh.
I love this right here.
What's that one guy's name? Linnaeus?
Huh?
No, never mind. No, this is Andreas Linnaeus.
Yeah, Knaus. See this right here? This OE. So this is, anybody ever take German?
No.
Okay, so you've taken it. So like I have to sing in it every so often. And this is a hard sound, but the way I've been told to do it, I've sung many things in German. What do you need? Oh yeah, Cole, can you help her get salad dressing? Can you show her where it is? Yeah, I did this with Abby too. Okay. Yeah, we've got some dressing. So anywho, the way I've been told to pronounce this OE combination is you make your mouth like you're saying the word book, but you try to say ooh. So it's like book. So he's Mussenbroek, right? And his lawyer friend, whose name was Andreas
I took one
Knaus.
class of German, and it was a semester, but it's like Spanish 1 for us sort of thing.
Yeah.
But like, I don't remember anything I've learned.
I've done several things in German, and the only one I ever had to do solo in German was the Lord's Prayer in German, and that was weird because there's the word in there for kingdom, and it's R-E-I-C-H, which makes sense because that's kind of like the Nazis had the First Reich, but we say Reich, and I don't know what they say. So I listened to a couple different recordings, and some of them were saying Reich with like a K, and some of them were saying like Reich with like a SH sound. So I finally that's how we say it in English. So I finally got in contact with a friend whose sister is a German professor, and she's totally fluent. And I was like, what is this? And she actually said it's the sound cats make when they hiss. So it's Reich. I'm like, great, I have to sing that. So anyway, German's fun. But I love this guy's name because it's Andreas Knaus, and rhyming names are just really fun. Andreas Knaus, and they were in Leyden, the Netherlands. So I guess this is Dutch more than German, but it's very similar. If you've ever heard Dutch, it's not quite like German, but like when we visited Amsterdam, we joked all the time. We spoke in fake Dutch for fun. We'd be like, we're going out, get the bakken pakken. We're going to take the bakken pakken. We might buy something. So Leyden jars could be joined together to store larger charges. So you can see here, this is an example of some Leyden jars. and they're joining them all together. And basically they're building a battery bigger and bigger and bigger, which is really kind of cool. So then we get Franklin, our dude, right? First American in the bunch. And in 1752, he flew the kite in the storm. Y'all know. Zap. Oh, now he didn't prove there was electricity, which is people would like, oh, he proved there was electricity. No, he just demonstrated that lightning was electricity.
Wait, where's Kermit?
So then we get,
Kermit the Frog.
Oh,
oh, Kermit. Yeah.
Oh, no.
And I love this picture of Ben because he looks like a real,
He looks like a warrior.
He looks like a wizard.
I was gonna say he looks like a
Warrior
badass.
of-
But he really does. He's like, oh, he does. He looks like a wizard. Yeah, I mean,
He actually did. He just killed them.
and he's got cherubs behind him
He just-
pulling on the kite
Actually
strings.
sitting out there like a
Because that happened. I mean,
The cherubs came.
yeah, so Ben was outside with the kite in the storm and all these naked angels arrived and they grabbed onto the strings and they, helped hold it down because it was so violent that his red blanket was blowing and, right?
That's his cape. Oh my gosh.
Yeah, but it's got no hood.
What's that second picture on the very bottom? That he's talking about the frog.
Yeah, so here's our guy we talked about last week. So when you watch, if you watch a class video from last week, I shared a link to this dude. Shh, guys, this dude is the Italian fellow Luigi Alonso Galvani. So Galvani was the guy who had the lab with all the time on his hands, and he had a bunch of assistants who were doing electrical experiments, and he was doing some
Oh, I know this is very
yeah, he was doing some dissection because he was a physician, but also a physicist. So he was dissecting this frog and his scalpel, his metal scalpel, picked up an electric charge. And when he touched it to the frog legs, they jumped. So we talked about this last week because there was a great video about him. And there's this little reenactment of him hanging little dissected frog legs from his cast iron fence in a lightning storm. And it's just great. Like, dude, what were you thinking? Right? All right. So then we got our Galvani guy. So Galvani made basically like a biological battery, right? He was the first one to show that muscles use electricity. So not only muscles, but your whole body, your entire process of anytime you move a part of your body, your heart beating, your thoughts, all of your neurological responses, everything's electric. And it gets down to like, are y'all okay over there? It gets down to if you ever look at videos of how, like, there are some really good YouTube videos that do graphic demonstrations of how hearing works or how your vestibular apparatus and your ears work, where there are all these microscopic hairs that actually they can be broken down even finer and finer, but there are points where they will move or shift, and there are even electrical processes in that.
Yeah.
I mean, everything comes down to it. So you got this dude again, the guy with the best name, Count Alessandro Giuseppe Antonio Anastasio Volta. I love the name.
Volta.
Count Volta.
Count Volta. That's what it's called.
Count Volta developed the first electric cell, and he called it voltaic pile because essentially it was a pile of things. Such an unattractive name for such an awesome, oh hush, such an awesome name for such an awesome, awful name for an awesome invention.
First battery was frog legs.
Alex, Cole, Michael. So you get this voltaic pile. Like I said, terrible name. So he had dissimilar metals, right? And then in between them, he put cardboard that he'd either soaked in like a salt solution or an acid. So if you think about how batteries work, that kind of should make some sense to you, why a salt solution or an acid would work, right?
Would I dissect a battery?
Actually, I think I'm going to take apart one of these if we have some time. So, because these are surprising inside. So Volta determined the best combination of metals was zinc and silver. So this is a diagram, and then this one is at the Smithsonian. Kind of cool looking too. So before we get into this British dudes here, I think, yeah, I don't know if I got enough activity out of one of these electrodes, but we'll give it a shot. So some of you guys were able to synthesize water, and everybody saw it. This may be a big fail, but we'll see. We will see. Yeah, I had one of my electrodes didn't do much. I don't know why. It just kind of sat there and looked stupid.
Why does he look so like his portrait's very off?
Who? Which one?
Johann Wilhelm.
Oh, Johann Wilhelm Ritter.
Johann.
Joanne. Where'd my corks go?
So like American, you know, like Joanne Wilhelm Reader. Joanne, what is it? Joanne.
So yeah,
Joanne Wilhelm Reader.
we got our dude at the top, and he's one of our English people, lots of them. So this dude is William Nicholson, and then he's friends with a surgeon, chemist and a surgeon are buddies. Now, surgeons in the 1700s, what did they do? Like, what kind of surgery? What did a surgeon do in 1700? Do you know? Yeah, they basically cut limbs off. Like, that was kind of their only job, right? I mean, they didn't really, what are you going to do? They weren't doing brain surgery or appendectomies or things like that on the regular. They were whacking off limbs. And if you didn't have a surgeon, you went to a barber, because the barber and a surgeon were actually quite similar.
The barber, except the barber also knew how to cut your hair.
The barber could cut your hair, pull your teeth, and if needed, remove a limb, but not preferably.
Different colors, different things.
Yeah. All right, I got the negative. Let's see if I can get this to.
What? What?
What's the matter?
No, we're not going down that road.
I don't think blood is on the thing though.
Blueberries.
No, not for barber. It's blood.
Bandages, right? Wasn't it bandages?
And the what's blue?
I don't remember.
Teeth. It's her teeth. It's blood. Bandages.
They pulled teeth.
Well, yeah, but what is the pull thing?
Maybe blue.
I don't remember that one.
Blood.
So let's see if it works. I don't know if it will because, like I said,
White teeth and bandages.
I kind of beat it up. That battery was terrible. So I definitely wanted to wear gloves here because I had put, like I said, pretty strong acid in here to just sort of help it along, speed it up. Nerd, come here. Because I don't have a rack. I didn't bring a rack in. So, all right, let's see. No, you can just pull the tops off for me. We get there. Great. So here we go. I got matches and all. I did bring them. Okay. You got them for me? So we're going to see if it goes. I don't know. I'm going to actually blow it instead of try shaking it everywhere like I did last time because that didn't work so well for me. So let's see if it works. It may not because, like I said, one of my electrodes was terrible. Oh, wait. I'm supposed to keep that one.
Yeah.
Wrong experiment. I'm thinking of the last one. Stupid. Okay, let's try the other one then. Here's the other. Well, we can see if it still works. Yeah. Let's see. Probably won't, but nope. This was a terrible. Let's try it better this time and I won't blow it out. Like that. There we go. Ozzy, don't die.
Don't die.
All right, let's try this again. Okay, ready?
I said I wasn't.
Well, take your time then, Michael. Just take your time.
I know.
This is the one I brutalized trying to get it out too. Oh my gosh, it was terrible. Okay, I'm gonna let my hand on fire.
Yeah.
Michael.
Don't play with matches. Did it help?
Maybe.
I have nails a little bit, kind of, not much.
Yeah.
Holy cow, Michael. Michael Foster.
No, it makes things worse. Just
Okay.
Ah, Lordy! Okay, wait. I'm gonna, I have a blade right here. Let me try that. I got an exact.
It's fine, but if it doesn't move and it's supposed to use the BB for you.
Yes, thank you.
Great luck.
I am from the Americas. I know how WD-40 works.
Classy. I'm classy.
Update the BB40. Here you get it.
Oh my gosh. No, I think this one's a
I
done
knew
deal.
it. I just didn't know if you were trying to do that in here first.
Do you think?
Oh, and that's the 42.
Maybe.
Oh, yeah.
Oh, my goodness. You can try one. You know there. Cole, help him get a toothpick.
Yeah, actually, no, there's one before.
This is ridiculous.
Can we get a corkscrew? Oh, my goodness, what did y'all do?
We brutalized it. Yeah. Cole, you want you to be a viewer maybe?
You're making me feel dumb.
We're trying to make it work. It's all this and it's probably not going to work. So that would be great. A corkscrew wouldn't work because you don't have enough resistance.
Do I have one of that?
All right, Michael's gonna try this.
How many pairs of glasses?
Here you go.
42.
Watch it just not. I'll listen. It won't work because it's terrible.
42. How many legs do you have?
Oh my word.
42.
42.
Oh, it's about got it. It's almost got it sideways. That'll work.
Corks are in that bottle.
Okay, here we go. Ready?
Yeah.
All right, guys. Let's see if it does.
We believe.
I don't know if it's.
The corks in the bottle.
I don't know if it's sideways enough.
It should be. Try one more time.
Michael, you're gonna get your fingers stuck.
Yeah, we give up.
Yeah.
All right, that was fun, wasn't it? Science. When it doesn't work, but you guys got it to go rather nicely. So back to our dudes. All right, we had our surgeon at the top and his friend, and they were able to separate water into hydrogen and oxygen by hydrolysis. So they would.
It's not sideways enough.
That's all right. So they were the first ones to do what you guys did today, which is pretty cool. And then this guy, Johann Wilhelm Ritter, he's the one who repeated the experiment and then discovered electroplating. So electroplating, you guys have anything plated on you? Maybe you're wearing something electroplated. Maybe you have something in the house. There you go. Is that electroplated?
I don't know.
I don't know. Maybe not. What might be around here? Lots of things are electroplated. For example, a lot of jewelry is silver plated. A lot of serving pieces. My silver set that's on top of the china cabinet in there is electroplated silver. So it just has a thin layer on the outside, right? Are y'all with me?
Yes.
Okay.
I'm listening.
All right. So then we get to this guy, Humphrey Davy. I love this name, Humphrey. But Humphrey Davy's important because not only did he do cool stuff, but he had awesome students. So Humphrey Davy, so now we are 1778 to 1829. So we haven't even gotten to the Civil War over here yet, right? And he took that voltaic pile that came from our count with all the names, and he was able to isolate elemental potassium, and then sodium and barium and calcium and strontium and magnesium. So this is a big deal. Then we get to my favorite dude here. Of all the electrochemist people, electro whatever, I like Faraday. I think Faraday is cool. So Faraday was actually Davy's lab assistant. So yay for Humphrey Davy for having an awesome lab assistant. Ozzy, Abby doesn't want you in her bed. So we're talking 1834, and Faraday came up with the 2 laws of electrochemistry. So the first one is that the amount of a substance deposited on an electrode of an electrolytic cell is directly proportional to the amount of electricity passing through the cell. And the second one is that the quantities of different elements deposited by a given amount of electricity are in ratio to their chemical equivalent weights. And as you can tell, the British think this is so awesome that they have put him on the 20-pound note. So if you are in the UK and you have a 20-pound note, you have our friend Faraday, who is pretty darn cool.
What do you do? What do you attribute to economics?
Well, I suppose electricity has helped make money for people. There you go. Bitcoin, way ahead of his time. There would be no cryptocurrency without Faraday. Fiat, so they put him on fiat money instead. I don't know, is British money fiat money? I'm assuming it is. Everybody's is, right? All right. So then Faraday, hanging out in his lab, just starts inventing words for things. Cool. Which is really cool. He just starts inventing words for things because truthfully, nobody had done what he's doing before. So he's the one that comes up with the word anode and cathode. And it's great because he has this written down in his notes in first person. So he wrote in his own words, the anode is therefore that surface at which the electric current, according to our present expression, enters. It is the negative extremity of the decomposing body, is where oxygen, chlorine are evolved, blah, blah, blah. Then he does the same thing with the cathode. And then he says, many bodies are decomposed directly by the electric current. Their elements being set free, these I propose to call electrolytes. I propose to call them electrolyte because I'm Faraday and I'm just writing the rules. And then I love it because this is also in first person. Finally, I require a term to express those bodies which can pass to the electrodes, or as they're usually called, the poles. Substances are frequently spoken of as being electronegative or electropositive, according as they go under the supposed influence of the direction of attraction. And then he says, I propose to distinguish such bodies by calling these anions, which go to the anode of the decomposing body, and those passing to the cathode, cations. And when I have occasion to speak of these together, I shall call them ions. Because he's Faraday, when I have occasion to speak of these together, I'm just going to call them ions. Love this. Cation, anion, and ions. So Faraday, dude, and I have a great image, if I have time to remember to show you, of Faraday and Daniel. This is Daniel, okay? John Frederick Daniel. And he's professor of chemistry at King's College, and they're contemporaries, Faraday and Daniel. King's College is still a big deal in London. It's a fancy schmancy place. Yes, sir.
The percentage just seems off.
The what seems off?
The John Frederick Daniel, professor of chemistry at King's College London, just seems a little bit off.
No, it's not a complete sentence, but
it's
but this is an outline, so it doesn't have to be complete sentences. So Daniel's research into development of constant current cells took place at the same time in the late 1830s that the commercial telegraph system began to appear. So it was his copper battery that then became the standard for British and American telegraphs. So any telegraph system that was initially in use is thanks to John Daniel. Now, here's where it gets fun. In 1839, Daniel experimented with fusion of metals with a 70-cell battery, and he produced an electric arc so big with so much ultraviolet light that it resulted in an instant sunburn, and it ended up seriously damaging his eyes and the eyes of the people who were watching. So science is cool. It's pretty blind. So he caused himself eye problems and gave himself a sunburn because he's like, I'm going to make a giant arc of electricity because why not, right?
No protection.
Yeah, because why not? So ultimately, he showed that the ion of a metal, rather than its oxide, carries an electric charge when a metal salt solution is electrolyzed. And these are some graphics of his copper batteries. And then we get to this dude, Walter Hermann Nernst. So Nernst studies electrochemistry, and he was inspired by the whole Arrhenius thing. Remember, we had the Arrhenius acids and Arrhenius bases, and the dissociation of the ions within the aqueous solution. So he gets really into this idea. He thinks this is super fun. So in 1889, he elucidated, I love that word. It always looks uncomfortable, like somebody put it in to try and make a big word, and it just never looks comfortable to me. But he elucidated the theory of galvanic cells by assuming an electrolyte pressure of dissolution, which forces ions from electrodes into solution, and which was opposed to the osmotic pressure of the dissolved ion. So basically, he ends up creating an equation called the Nernst equation, and it relates to the voltage of a cell. And if you look here, it says electrolytic pressure of dissolution. So when you're talking about electricity and pressure, you're talking about volts every time, right? So you can almost think of it as electric pressure. So he ends up coming up with an equation that's used to talk about voltage of a cell and its properties. And then I love this. This is why I think Faraday is so freaking awesome. I'm sorry, but look at this man. First of all, he's got a cool looking steampunky thing on the table, which I'm all about. Secondly, that bow tie is massive, but it's on point. Like a smaller one would look stupid. Third, the watch chain on the vest. Ooh, sweet. And then look at that. Look at that coat, y'all. That coat.
That's a nice coat.
No lie. I mean, that coat is, it's double-breasted buttons. Look at that. I mean, really, for real, dude. And then the hair. You gotta love the man's dude.
Why do they all do that pose? Like they always like.
Because they're very serious, Cole. They're serious
That's their
scientists.
invention, and then it's like, where's the jacket?
He's got his glasses in his hand. Or is that a monocle? I don't even know. Maybe it's not a glasses. Maybe it's some, I don't know what it is. But he's awesome. I love Faraday. Anyway, you can look up videos of Faraday cages. Very fun. Very fun. No, not those. So the terms that go along here are voltage, which we talk about potential difference between two cells is the amount of energy that drives a reaction. And think of it as electric pressure, right? And then we have current. Remember, current is the flow of electrons, and it's electrons per second. And you don't have to have high voltage to have a high current. You can have high voltage and a low current, or the other way around. So one of them is how hard it's being pushed, and the other is how fast it's actually moving. And they're not quite the same thing, and they don't have to be, the relationship doesn't have to be parallel there. So then you have primary batteries, which we also call galvanic cells, right? And secondary batteries, which we call electrolytic cells. And then we also have tertiary batteries, which are not really batteries so much, but fuel cells, which are different. So here's your galvanic cell. So your galvanic cell, which is voltaic, it's a type of voltaic cell. It induces a spontaneous redox reaction to create flow of electrical charges or electricity. Non-rechargeable. So these guys we use today are galvanic cells, right? They contain all of the reactants and they induce a redox reaction. And that flow of electrical charges is what gives us the power to run whatever you would put this in, a toy or whatever, right? Now these run out, don't they? When the reactants are gone, the battery is what? What do we call it?
Dead.
Yeah, dead. The battery's dead. You ever had a kid around you with a toy and the battery's dying and the toy's like, you ever heard that? It's awesome.
Yeah.
And then you know that peace is coming because the battery's going to die, right? So that's what happens when all the reactants are used up. So any of the cells that you would buy in the grocery store in the checkout line by the Inquirer magazine, those are all your galvanic. So your electrons go from the anode, since negative, since electrons are built up there, to the cathode, positive, since it's gaining electrons. And your galvanic cell produces electrical charge from the flow of electrons, and the electrons move due to the redox reaction. So remember, it's spontaneous redox reactions, and they already have all of the reactants inside, right? We don't need to feed them. And examples would be all the kinds of things that you're familiar with as far as batteries that are disposable batteries, right? Non-rechargeable. A's, double A's, D's, C's, 9 volts. And then any non-rechargeable battery, you can pretty much lump that in with the idea of galvanic cells. So here is a graphic about a fuel cell. Now, fuel cells are a little different. They have to be fed. So you've got conventional batteries that supply electrical energy from chemical reactants stored within them. That's these, right? And when the reactants are consumed, the battery's dead. An alternative would be to feed the reactants into the cell as they're required, so as to permit the cell to operate continuously. In this case, the reactants can be thought of as fuel to drive the cell, so they are fuel cells. And fuel cells were not employed practically until we started space exploration. Yep. So the principle was demonstrated in 1839, but we didn't do much with it till the 1960s. We didn't find a use for them. Y'all with me over there on the couch?
Yeah, I watched.
So this dude, Sir William Grove, who's a Welsh lawyer and amateur chemist. So I was telling the other group, you'll notice that a lot of these guys that come up with these amazing thoughts, ideas, concepts, discoveries, inventions, a lot of them are dudes who had time on their hands. They were either independently wealthy or they had a job that paid them well, and that allowed them the time to do this kind of stuff, which is good because this has improved our lives, no doubt, right? So that's why you often see these types of personalities over and over again. So this Welsh lawyer guy, you ever heard Welsh spoken?
Yeah.
Oh, that's a fun language. So this Welsh guy, chemist and lawyer, at the time, it was already known that water could be decomposed into hydrogen and oxygen by electrolysis, which is what we did. And he tried combining the two gases in a simple apparatus, which is what you did as well, right? And he discovered what he called reverse electrolysis. What's another word for synthesizing water, creating water? So condensation you'll often see in chemical reactions when water is formed. You'll often see it termed condensation, which makes sense because, if you just think about water forming on the outside of your glass, it's not really forming there, it's just condensing. But because that's the word that's been used, it then applies to chemical reactions as well. So he called this reverse electrolysis, and it caused a potential difference to be generated between the two electrodes. So it was not until 1959 that the first working hydrogen oxygen fuel cell was developed by Francis Thomas Bacon, another British dude. So modern cells employ an alkaline electrolyte so that the electrode reactions differ from the one shown, this one here, by the addition of hydroxide to both sides of the equations. And then although hydrogen has, now this is interesting, so although hydrogen has the largest energy to mass ratio of any fuel, that is hard to say, energy to mass ratio of any fuel, it cannot be compressed into a liquid at ordinary temperature. So it's not practical, right? So if it's stored as a gas, the very high pressures require heavy storage containers. Now it's impractical in this way too. And that greatly reduced the effective energy density. Some solid materials capable of absorbing huge amounts of hydrogen can reduce the required pressure. And other fuels such as alcohols, hydrocarbon liquids, and even coal slurries have been used. And methanol appears to be an especially promising fuel. When did we use methanol this year? Do you guys remember? We used it in the lab. It was a demo.
Was it the flame one?
Yeah, it was the flame one, Michael, right. We used methanol as a medium to burn the chemicals. So here are galvanic cells again, and we get corrosion. So did anybody's battery corrode? Yeah.
Maybe.
Yeah, the one I had, this is the one I did last night. And when it corroded, it clearly has some blue on it. Y'all can pass it around, but don't stick your hands on the corrosion part. So what is that likely to be if it's got blue on the top? What element is that? Probably
Zinc or copper.
copper. Yeah, think about it, because and there's probably zinc in there too. But when you see that blue, there's your copper, right? So bronze, as we were talking about before, I think with the other group. So bronze has copper in it, right? Bronze is an alloy. Remember, Alex? Bronze is an alloy, and there's copper in it. What happens to bronze when you leave it out in the elements?
Does it turn blue?
Yeah, it oxidizes, right? It turns blue. What color is the Statue of Liberty?
Greenish?
What color is she really?
Wow.
She's bronze. Yeah, if you were to clean her off, she would be bronze. But she's oxidized, especially because she's by salt water.
And
The
she,
city of
and
New
she,
York never cleans it because if they did, like within a month or two, it'd be the same color.
They cleaned it when I was a kid. And I remember because it was my first trip to see my great grandmother in Nova Scotia. And we drove through, and we drove in such a way that we were supposed to be able to look out in the water and see it. And it was covered, said she's trying to show you. And it was covered in scaffolding because they were attempting to clean it. And, you know, I don't think it stayed clean, but for a hot minute. And then it was right back to where it was. Yeah.
that is better known as green.
Yeah, so this is bronze. And if you look at this, do you see where it's oxidized as well? See the green?
Yeah.
And I intentionally don't clean it because it's pretty right there. So anyway, galvanic corrosion is an electrochemical process in which one metal corrodes, preferably when it is in electrical contact with another in the presence of an electrolyte. So that's what we had going on with these guys. So there's a little graphic. What is voltage? Again, think of voltage like pressure, electric pressure. This dude is pushing. There's your pressure. And then your current is the flow, right?
Looks like he's trapped in the back.
Yeah, he is. He's a mime. He's doing the mime thing, you know,
Yeah, the
trapped in the
mime. That's
box.
what I'm saying.
Yep. Uh-huh. So then we have electrolytic cells. Electrolytic cells are different from galvanic in that they are rechargeable. So think about this. These guys here turn stored chemical energy into moving electric current, right? Okay. Electrolytic cells, your rechargeable batteries, take moving electric current, turn it into stored chemical energy, and then turn it back into moving electric current. So if you have a laptop, a cell phone, an MP3 player, anything at all that is rechargeable.
So does that mean one that is built into design is being rechargeable? Like for example,
Yeah.
our car battery you can recharge.
Mhm.
It's not an electrolytic cell,
Designed to be.
not designed.
Mm-hmm. So,
Well, actually, it kind of is though.
well, They used to have ways to recharge your like A batteries and whatever.
Well, I was gonna say, aren't
It's
our
terrible.
batteries technically kind of, because they have, because of the alternator?
Kind of, maybe, yeah. So an electrolytic cell is a cell which requires an outside electrical source to initiate the redox reaction. So it's not spontaneous. You have to initiate it, okay? And the process of how electric energy drives the non-spontaneous reaction is called electrolysis. Whereas the galvanic cell uses a redox reaction to make electrons flow, electrolytic cells use electron movement in the source of electricity to cause the redox reaction. In an electrolytic cell, electrons are forced to flow in the opposite direction. So you have to force the redox reaction in an electrolytic cell as opposed to a galvanic cell where it is spontaneous. So your electrolytic cells is one kind of battery that electrolytic cell is one kind of battery that requires an outside electrical source to drive the non-spontaneous redox reaction. Rechargeable batteries act as electrolytic cells when they are being recharged. So here's the thing to think about. The rechargeable ones, like the laptop or your phone, act as an electrolytic cell when it's being recharged. When you're draining it, it's acting like a galvanic cell because you aren't feeding it, it's using the reactants inside and the reaction's spontaneous. Does that make sense? Yes, clear as mud. So a reaction's non-spontaneous. This is about Gibbs energy again. Remember that? Oh Lord, not that, right? And you must supply electrons to the cathode to drive the reduction. So the cathode is negative. Because it's backwards, right? So then you must remove electrons from the anode to drive oxidation. So now your anode is positive. Oh, fun. Now once we thought we knew something. Just when you thought you knew what was going on.
That wasn't me.
So that's because this is the process that occurs while it's being recharged. So if it's, you guys good? So if it's the process that occurs while it's being recharged, you can kind of think as the recharging as the reverse of the battery itself draining, which makes sense, right? You have to have the opposite process to put stuff in than you do to take stuff out. And then your electrolytic cells turn electrical energy into chemical energy. And then once they stop being charged, they act as galvanic cells and turn it back into electric energy. So your most common ones are the ones you think of that you have to recharge all the time. Your phone, your computer, all that kind of business. And while the battery is in use, it's acting like a galvanic cell. And it's using redox energy to produce electricity. And while the battery is charging, it's electrolytic in function, right? So it's the flow of electrons from your wall outlet that give the energy for the redox reaction for it to behave as an electrolytic cell, because it's not spontaneous. You have to force it. And it's the flow of electrons from your wall outlet that forces it. And there's a good example there is, charge my phone with my lightning cord. So in electrolysis, a compound is decomposed, usually into hydrogen, oxygen, aluminum, sodium, calcium. So I'm sorry, chlorine. So these are among the elements that can be isolated. You did it today. You isolated hydrogen and oxygen. Okay, what happened when you put the match inside the tube that contained the hydrogen? The one that you just blown out, the still glowing match. Did anything happen?
No.
Yeah, nothing should have happened. Should just gone petered out. Now, if you were able to do it correctly, if you took your still glowing match and held it above, are y'all okay over there? Goodness sakes. And held it above the tube with the oxygen, what happened? Did anybody get anything to happen in that case?
Yeah, it just popped and then the flame grew.
That was the second one. That was when you did the synthesis of water, right?
No, both.
Oh, that was both? You got to pop both times?
We got a pop on the hydrogen.
Oh, you did?
Me too.
Okay. All right. That's interesting.
We got like a weird whistling type noise on the oxygen.
Usually, if you have enough oxygen in there, you can get it to relight just from glowing. Because, if you think about it, oxygen is what fire eats, right? So, by the way, if anybody ever lives with anyone, who has an oxygen tank, you have to be extra careful around them, right? Because they're a big fire hazard. And you should also have obnoxious signs all over the doors to your house that say oxygen in use. One of my dearest friends has kids who have oxygen in use at night. And she didn't want to put the ugly sign on her front door. And I'm like, look, dude, my brother-in-law's a firefighter. Do you know what happens when there's oxygen in your house if there's a fire? Like, he needs to know that. People need to know that before they go in. So you always have to be careful. And there was a comedian once who did a whole bit about airlines. And he talked about how they talk to you like you're dumb, and the oxygen masks will come down like magic, and you put them on your face. But his favorite warning was the one that said, before applying oxygen mask, extinguish your cigarette, which was back when you could fly on the plane.
Oh, yeah, that's
So-
a bad idea.
I mean, smoke on the plane. So think about the people who would be smoking their cigarettes and putting their oxygen masks on, blowing up. So yeah,
Put it out, yeah, hold on.
smoking's bad. Don't do it. Electrolysis. So this is what we did in lab. It's a process by which electrons are forced through a chemical cell, thus causing a chemical reaction. Positive charge usually attracts electrons, and the electrode providing electrons is called the cathode, and the electrode, I cannot read, the electrode providing electrons, it was called the cathode because reduction takes place at it. So a layer of second metal, this is when we get into, electroplating. All right, so have you guys, we talked about electroplating briefly. Do you guys know of something in your house that's electroplated? I made the younger group go find something in their house that's electroplated.
What is
So-
the like full definition of electric?
So basically, I have a video that's a how it's made video. I could watch how it's made all day
I love
long.
how it's made.
Yes, me too. I could binge how it's made easily. But basically, they'll put an object to be electroplated into a bath. It's usually like a salt bath, and it'll have a current going through it. And it will have either bags full of balls or bars of the metal they wish to plate onto another. And they will dip these pieces of metal or whatever they're plating in and run current through the bath through them. And all these little ions of the metal they're wanting to plate will flow and just stick. And so you get this perfectly thin layer of metal on top of whatever you're electroplating, which is pretty cool. So it's the process of plating one metal onto another by hydrolysis. And it's most commonly for decorative purposes or to prevent corrosion of the metal. There are also specific types of electroplating, such as copper plating, silver plating, and chromium plating. So a lot of the times you see cars with chrome bumpers or chrome pieces, they're chrome plated. And silver plating, right here. This is a good example of silver plating. It's dirty, super dirty. I need to clean it. Why is it dirty? What's happened to the silver? Yeah, it's silver. Yeah, so we've got oxidation, exactly, of the silver.
That's right, yeah,
They'll go
clean
black,
for
right?
Those little cups we have, those clean before next time equipment.
Yep, I do. I always clean them up. But if you can get it clean, oh, actually, there's a tiny bit of acid in my water here. If you can get them clean, they're a beautiful silver underneath. Yeah, it's getting more. But this is plated. This is silver on top of what I think is bronze or something like that, because you can see in some places a more copperish color come out. So yeah, a lot of stuff like this, or silverware, that's actual silverware, is plated. It makes it less expensive and more durable in a lot of cases. And there is gold plating too. You get gold plated jewelry or whatever, which makes it way more expensive. You can take your random, like, ladies, if you have any gold earrings where you are missing an earring, like I had a couple like that, I lost one. And you can take your mix match gold pieces to the jeweler and they'll give you cash for them. And it's surprising how much you can get for a handful of stuff you can't use anymore because it's missing pieces or whatever. So you can you can electroplate onto metal or even plastic. So here is how it's made for electroplating. And it is pretty cool.
Plating is a layer of metal coating an object of a different type of metal. The purpose can be decorative, as in silver plating, or practical. With industrial parts, for instance, zinc or cadmium plating prevents the underlying metal from rusting, while nickel or chrome plating protects against wear. You can plate almost any type of metal. Let's follow some steel aerospace parts as they're about to be plated with cadmium to make them corrosion resistant.
Oh, aerospace.
For the plating metal to bond properly, the steel surface must be free of contaminants such as oil and grease. Workers suspend the parts over a vat of boiling chemical solvents. As the hot vapor comes into contact with the colder metal, it condenses, dripping down into the vat and taking any contaminants along with it. The remaining solvent residues evaporate, leaving the parts squeaky clean and dry. Next, a worker wearing protective clothing sandblasts the parts with aluminum oxide powder, a strong abrasive. This roughens up the surface so that the plating metal will adhere better. The most common plating metals for industrial purposes are zinc, chrome, and nickel. Think motorcycle parts or sink faucets. Decorative items, on the other hand, are more likely to be plated in tin, brass, gold, or silver. Traditional tea sets, for instance, are often made of silver-plated copper or zinc. The plating process is called electroplating because the key to it all is electricity. They start by tying strands of copper wire to a copper support frame. Copper being the best metal for conducting electricity.
That's an expensive wheel of wire. Copper is so
Then they
pricey.
attach the steel parts they'll be plating. When they hook up this support to an electric current, electricity will run from the support through these wires right to the pieces. They do the electroplating in a tank. After filling it with water, they add a handful of chemicals to help conduct electricity, because
Probably
water
salt and
alone
acid,
won't
stuff
conduct
like
it
that.
sufficiently. Along the sides of the tank, in bags, are metal baskets. They contain bars or balls of the plating metal, in this case cadmium. Workers connect the support frame with the steel parts to the negative terminal of an electric source, the baskets of cadmium to the positive terminal. Then they switch on a steady DC current, no stronger than 6 volts. The electricity dissolves the cadmium, lacing the particles with a positive charge. They travel through the water and attach themselves to the negative charged steel parts, creating a smooth and even layer of cadmium. Thin plating requires just a few minutes in the tank, thick plating several hours. Then workers rinse the parts in water for about a minute to remove the chemical residues. To make the parts even more rust resistant, workers immerse them in a series of compounds. This triggers a chemical reaction in the plating, enhancing its ability to withstand corrosion. This reaction, however, changes the colors. A final rinse in hot water, and this cadmium-plated steel aerospace part is finally ready. From start to finish, the process has taken about 90 minutes. To plate with chrome or gold, they have to use a chemical compound containing gold or chromium. That's because electricity can't dissolve solid chromium well enough, and it can't dissolve solid gold at all. The compound dissolves in the bath like salt, but then solidifies once it reaches the object being plated. Metal plating is very durable, but if subjected to a lot of wear and tear, the object will eventually have to be replated.
I love how it's made. It's the best. Yeah, it's always great. So, watches.
And I think it was like Rolex or something. I think the guy was Rolex or something.
I
It was
could
really cool.
seriously watch how it's made all day long. All right, do you have your homework and we can go over it?
I didn't see.
I'll give you guys a second to get it out. So this was keep in binder, so you should have it with your, I think it was, wasn't it? This is little guys. This was. Just tad. So today, just a bit, a wee bit. Yeah, that's true. Ethan like begs to have class on the couch, and then he's doing this the whole time. So
You should let everyone come out.
this couch. So when we bought this house, we did not bring the furniture from the old house because I'm sorry, but 2 little boys had absolutely destroyed it. I mean, destroyed it. It was, they had done gymnastics on it for years, and it was jacked. So yeah, I mean, for the last year we lived in that house, we knew we were going to be moving. I had a piece of plywood under the cushions on the couch because they had broken all the springs. So yeah, so we bought these, and it took me forever to find what I wanted, but that piece you're in, it's called a cuddler. That's what they called it, that end piece. And I'm like, that is where I'm going to sit for the rest of my life. That is a comfy spot. And that was actually a sofa, and it's pretty comfortable for a sofa. So how do an acidic dry cell and an alkaline dry cell differ? What answers did you guys get? Anybody want to tell me what they got? Abby. Okay. Anybody else have anything different?
There's also, they'll have different components in them.
There you go.
Yeah,
Mhm.
ours was the carbon cathode in a alkaline cell is replaced by a piece of brass.
There you go. Yeah,
and
there's.
ammonium chloride is replaced by potassium hydroxide.
Yeah, so there are several differences. So the book answer, I think, tried to cover as many as possible. So I said the materials are different, right? So in an acidic dry cell, the carbon rod and zinc case are used along with NH4Cl, which is an acid. And in an alkaline dry cell, a base rod and a zinc case are used along with potassium hydroxide, in which case alkaline dry cells tend to last longer than acidic dry cells.
NH4 is nitrogen potassium.
NH4 is, no,
What is it?
nitrogen, potassium, no.
What is it?
NH3, you're thinking like ammonia? Is that where you're going with that?
Just, yeah.
Yeah, but that's separate from,
I
that's
just can't remember.
sodium, wait a minute, what is that?
Which
Sodium
one?
hydrochloride,
Which one are you looking
NH4Cl. So describe how standard electrode potential is measured. Who
at?
has
That's
it?
not sodium.
Oh, nitrogen, sorry. Nitrogen. My brain's dead today. Sorry about that. That happens to me every so often. You know, one day when I swear, one day when they stop changing my medicine every 3 months, I will get the brain back that I had years ago. But maybe I'm dreaming. Maybe that'll never happen. And I will be a screwball forever. So describe how a standard electrode potential is measured. Who's got that one? I know Abby has it. Who else has it? Michael, what have you got?
Which one?
4. Oh, yeah, 4.
4. Okay. Zinc corrodes the easiest because of its low electronegativity.
That's not.
That was 6, I think.
6?
Or was that?
No.
No, that was 8.
What?
I don't know. 4. Describe how standard electrode potential is measured.
No, we did 2 courses.
We said we
No.
did.
So Abby, what do you have?
I was not sure about this one. I put the, I guess it's the equation that the electric potential of the cathode minus that of the anode is.
Yeah.
So
Yeah. So connect a standard hydrogen electrode to a half cell in which the reaction of interest happens using a salt bridge. They're talking about like the whole process here. So the voltage of the electrode with respect to the standard hydrogen electrode is the standard electrode potential.
The standard.
Yeah, that was kind of, let's see if we can figure it out answer.
The standard hydrogen electrode has like platinum and some other things.
Okay.
But I remember platinum was part of it.
Okay, cool. So calculate the voltage and identity of the cathode for a cell in which the natural reaction between the following electrodes happens. Did anybody get this one?
I got the answer.
Number 6. So it says calculate the voltage and identity of the cathode for a cell in which the natural reaction between the following electrodes happens.
I
Zinc
got
is
that
the cathode.
zinc was cathode and that the voltage is 0.001 0662.
That's exactly what we
That's
got.
what I got.
There you go. Look at that. You guys are pretty darn good. So your cell voltage, and there's your zinc right there. 0.66. You got 0.62. Zinc electrode is the cathode.
0.0662.
662. Okay, they just left it at 66.
Yeah.
There you go. All right, so a sacrificial anode is allowed to corrode.
Oh, yeah.
Why is the use of a sacrificial anode considered to be a way to prevent corrosion? Yes. What you got, Abby?
The sacrificial anode gives electrons to the cathode, which further stops the corrosion of the structural metal.
Does anybody have anything different? Thereabouts.
Basically, yeah, the corrosion
Thereabouts.
of the anode stops or slows the corrosion of the important metal.
Yeah. This one was terrible for me to try and print. But it said using a sacrificial anode is a way to prevent corrosion because the anode is connected to another metal, which is usually an important structural component. The metal is protected from oxidation as the anode gives up electrons to the structural metal because the sacrificial metal oxidizes more easily.
You really compacted that.
I know, I didn't write that. That came from your book. But I had to squash it to make it fit. All right, so now on to the next section where we had 1, 2, 5, 6, 13. So 1, how does an electrolytic cell differ from a galvanic cell? Cole.
Galvanic cells generate electrical energy, but electrolytic cells consume energy.
Yeah, that's a good way to put it. You're right, in that it's taking the electrons in, right? Does anybody have something different?
One
Yeah,
is
what you got?
basically the inverse of the other.
What'd you get, Shannon?
Galvanic cells are not rechargeable.
There you go. Jack, do you have something different?
Yeah, but now I'm not confident in this. I don't.
Well, just say it.
Galvanic cells gets its energy from spontaneous redox reactions.
Yes.
Electrolytic cells involve a non-spontaneous.
Yes, that's perfect. Yeah. So your galvanic cell generates electric current spontaneously from a chemical reaction, and an electrolytic cell electrical energy uses it to cause the reaction to happen. That's, you guys all together gave a very thorough answer. So what chemical process occurs at an anode of an electrolytic cell? Yeah, Cole.
Oxidation.
Okay. What do y'all have?
No. Electrolytic, it would be reduction
Why?
because it's the inverse. It's opposite.
Hey.
It would be-
So yeah.
It's not an ox.
This one says anox. So that's where I'm confused too, because I thought the same thing you did, because it's the opposite. It's the inverse. But I guess I don't know if it's asking about the electrolytic cell when it is behaving electrolytically, or the electrolytic cell that is now being used like a galvanic cell, because
In which case you could just put down either answer and it'd be correct.
yeah, so this one I didn't love as much, but I was curious to see what you all thought. So list 3 commercial products used by made by using electrolytic cells. This one was easy. So what'd y'all come up with?
Aluminum and sodium are both gotten by it, and electroplating also.
No, made by using electrolytic cells, not electroplating. Were you talking about electroplating?
Aluminum and sodium are both created.
Oh, you're talking about creating them through Okay.
That's how.
All right. Yes. Okay. Yes. I thought you were heading down the electroplating road. What'd you get, Allie? Abby?
Aluminum, copper, and zinc.
Mm-hmm. What'd you
She
get?
said we found refining copper,
Mm-hmm.
and in the book it actually talked about how it's necessary to make an ingredient of nylon.
Okay. That's interesting.
And another one was just production of chlorine.
There you go. Chlorine. Yes. So yes, you can do these things where you can isolate particular elements for production. And then also you've got all of these kinds of products which contain them as well. So it listed sodium, metal, chlorine gas, aluminum, hydrogen gas. There you go. So what does electrolysis mean? What's it mean literally?
Oh, 1 second.
Or is it?
I can answer that. It's
When by electricity.
electrolysis.
Go ahead.
The process in which an electric current is used to produce a chemical reaction such as decomposition.
Right. And Alex is right, is that it's splitting by electricity, right? Perfect. Okay, so they gave you this reaction and said it happens naturally. Explain why it's necessary to use an electrical current to deposit a layer of zinc on the copper bracelet. Did anybody come up with this one?
so that you can control
The oxygen.
how much is put on.
Okay.
What was the question?
So it said the following reaction happens naturally, and there it is. Explain why it's necessary to use an electric current to deposit a layer of zinc on a copper bracelet. So this one's hard to read, but to deposit zinc on a bracelet, the zinc, sorry, must be dissolved in a solution and the copper must be in solid form. So the reverse of the reaction shown is needed. If the reaction happens naturally in the direction shown, then an electric current is needed to cause the reverse reaction to happen. Because if you are endothermic one way, you think about it that way, right? And you're gonna be exothermic the other way. What are you talking about?
No.
Yeah, that's what I thought. So, yeah. So before I move on to your test next week, test for this upcoming stuff, I wanted to, not here, would it be there for me, fastest for me to go this way? Maybe. Real quick, I'll show you what's coming. We're getting into the stuff that I get super passionate about and thoroughly enjoy. So yeah, this is where it gets fun. At least I think more fun. So we're almost there. I showed you this last week, I think. So we're in Q4 here, and we are about to do, we just finished lesson 28. All right, that's this we just did. Come here. I can't make you bigger if you hide from me. There we go. So you have 2-week break, right? You're going to get your test available to you this afternoon. Also available to you this afternoon is an assignment in Teacher Ease where you can go online and enter the element you want to do for your final project. I entered the ones I already knew, but the others still need to be entered. And it's a discussion topic in Teacher Ease. So you just go in and comment. That way everybody can see what everybody else is doing and nobody accidentally does something somebody else is doing. So both of those are going to be due by the time you get back. And then when you get back, we've got the fun nuclear chemistry bit, which really isn't, it's going to be kind of quick.
Yeah.
And we'll be in and out of it, I feel, pretty quickly. And then we're going to start into the organic stuff. And the organic chemistry is leading us into biology. Perfect for a lead into next year. If you don't know if you're coming back next year, we still have 1 or 2 spaces. So most of this class is coming right back. Plus we're adding at least 1, possibly 2. So that'll be great. All right, so I'm gonna kill my screen share so that it can't be seen on here. Huh?
What did it ever do to you?
What did it ever do to me? I don't know, man. And then I'm gonna kill this too, so that I can do some test review with you guys. If that's okay, that is. If you want a test review, you usually do want a test review. All right, so, oh no, don't go there. Don't do that. Okay. Login. And everybody should have gotten the email from me. You all did, right? With your grade? I explained that at the beginning, didn't I? Okay. I know I talked to the other group about
Those are
it.
the only ones that are getting dropped, right?
So far, if you get something lower than those between now and the end of the year, I'll replace it. Correct. By the way, I had to, in order to sort that, I had to use Excel. So I essentially had to take, it has some great sorting options in Teacher East, but it didn't have that one that I wanted.
Lowest?
So, well, it does lowest, but the problem is that okay, so I have to give it a threshold. So I'll say, okay, lowest is a 60. But then if you have above a 60, it's just not going to show anything for you. So maybe your lowest was a 61. So now I have to raise the threshold again, which means I see everybody whose lowest, you see what I mean? Was below a 61. So it just gets to be a lot. So what I ended up doing was putting the threshold at, A+ or whatever. And then I put every assignment that's been graded, and then I had to sort them by homework or whatever, take those out and sort it. But I had almost 1,400 assignments that I've graded already from the beginning of the year.
Everyone did, because you did everything like 12 or 20 times.
Mm-hmm.
Yeah.
1,400. I was like, oh man, my life is crazier than I thought it was. I knew I was nuts, but was I really that nuts? So this will be due when you return on 4/13. This one has a fair amount of questions. It has 36.
Oh my God.
36 questions. So if you want to take notes, it's an hour. Mhm.
36, wait, what?
You'll be fine. 36 points. I'm sorry, 14 questions. I have to open it to see that.
Oh.
36 points, 14 questions. Sorry, I know y'all are about to die. We still have to read it all. So
14 questions, 36 points. That's good.
we have some matching, and the matching is going to involve oxidation and reduction. So I'm not going to ask you to state the definition of oxidation or reduction, but I expect you to be able to recognize which goes with which, right? So let's do it this way. If I say oxidation is the, you say what?
Loss.
The loss of what?
Electrons.
Which means the charge becomes more.
Positive.
There you go. And reduction is the
Gain of
gain,
electrons, making it
which
more
means the
negative.
charge becomes more negative. Oh, you guys have it down. All right. So then what is the, so somebody explain to me, what would I be asking for if I said the total number of electrons that an atom gains or loses in order to form a chemical bond with another atom? What would I be talking about? If I gave you the hint that it's also called the oxidation state and told you it was 2 blanks.
Could you say the whole question?
So it's the blank blank, also called the oxidation state, is the total number of electrons that an atom either gains or loses in order to form a chemical bond with another atom.
Oxidation energy, something like that.
Oxidation number. Yeah, easier than it sounds. Oxidation number. All right.
One they have to write down, or is that multiple choice?
You have to find me.
That one's a write down.
Okay.
Hey, well, that one's oxidation number. No, I haven't asked you to find it yet. That was just telling you to be able to recognize it. All right, now, what do you call either the oxidation or reduction component of a reaction? You have to break it out to do these kind of equations. So what do you call it?
Agent?
Not the agent. When you take just the oxidation, half reaction, just the oxidation component or just the reduction component, it's a half reaction, right? All right, and how about if I asked you if it was true or false that the reducing agent removes oxygen from another substance or adds hydrogen? Reducing agent removes oxygen.
I'm gonna say false.
That would be true, right? And if I said the oxidizing agent removes it, that would be false.
No, I'll get that.
Because remember, oxidation involves loss of electrons, which means it's what?
Gaining charge.
There you go, there you go, there you go. All right, so what do you call the potential difference between electrodes? It's also electric pressure. Yes, voltage, good. And if I gave you a match question with anodes and cathodes, would you be able to identify where reduction and oxidation occur?
Probably.
Anox, red cat. Anox, red cat. Get it in your head and you'll have it. Anox, red cat. And then let's see. We just talked about that one. So now I will ask you to give the oxidation number in a particular, I'm going to show you a reaction written out in media so that you click the media file and see it. And I'm going to ask you to identify the oxidation numbers for each of the components. Okay. So I'll give you a hint. It's one you've done before in your homework. So if you be sure you understand the ones in your homework, it will look familiar to you. And then you need to be able to identify whether it's a redox reaction. And there will be another one and you'll need to identify whether it's a redox reaction. And again, your hint is you've done it before, it's in your homework. If you pay attention to what your homework was, go back and look at it, you'll get that. All right, and then galvanic cells, you guys are pretty good on. You're gonna have to name an example of an electrolytic cell, which I'm sure you could do in your sleep. And I'm sure you guys could explain what is electrolysis also in your sleep. So it is now 1:30 and it is Jackie's time. So I will say goodbye here. So no, we're good.